Now that we have laid the foundations for probability, let's summarize some of the most common and useful rules pertaining to these event relationships and operations. When we wish to find the probability of the union of two events, the additive law can be very useful. Note that we add the probabilities of each respective event, but we must subtract the probability of the intersection. If the two events overlap in some manner, not subtracting the intersection would count the probability of the intersection twice. If the two events are mutually exclusive, the addition law reduces to the sum of the probabilities, since the probability of the intersection of two mutually exclusive events is known to be zero. If we wish to find the probability of the intersection of two events, multiply the probability of the first event by the probability of the second event, but be sure that the probability of the second event is found knowing that the first event has already occurred. The vertical line between the second and first event is the symbol for conditional probability and is read as the probability of B given that A has occurred. If the two events are independent, then there is no influence on the outcome of one event based on the outcome of the other. In this case, the multiplicative law reduces to the product of the probabilities of each event. In other words, the probability of B given that A has occurred becomes the probability of B, since A has no influence on B. Contingency tables are excellent ways to organize data and determine compound and conditional probabilities. Referring to the table here, the probability of a meat eater and a female would be 22 over 197. The probability of a vegetarian would be 119 over 197. The probability of a female given a vegetarian would be 88 over 119. And the probability of a vegetarian given a female would be 88 over 110. Note that the last two results are not numerically related based on the order of the arguments in the conditional statement. In general, this will not be true. A useful rule in probability to classify a probability as statistically significant or not is the rare event rule. If the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect, we conclude that the probability is unlikely of occurring. In most organizations, we define this region to be more than 2 standard deviations in magnitude from the mean. This constitutes a probability less than 0.05. If a number of occurrences has a probability less than 0.05, then we conclude that this number of occurrences is a significant number of occurrences. Recognize that the 0.05 criteria is based on the risk attitude of the organization and subject to different interpretation. When sampling without replacement, and the sample size is no more than 5% of the size of the population, we can utilize an approximation and treat the selections as being independent. This greatly reduces the complexity of our calculation. This idea also plays into redundancy of mechanical designs. If we design in redundant or parallel systems, our chances of a catastrophic failure drops significantly, based on the likelihood of failure raised to a power represented by the number of redundancies. For example, suppose 15% of adults in the country use a hookah. We know that there are 250 million adults in the U.S. If we select 4 people at random and want to find the probability that the 4 adults all use a hookah, we can deploy the 5% guideline. Since the sample of 4 is much less than 5% of the population, our answer would be 0.15 to the 4th power, or 0.0005. In probability, knowing how to count is extremely important. I know what you are thinking. Of course I know how to count. Many of the problems we face in industry require more elaborate methods to determine the total number of possible outcomes. The multiplication counting rule is for situations where there is order and replacement. In general, we can have several elements, each with a different number of selections. Taking the product of all the possible outcomes for each element gives the total number of possible configurations. The factorial rule helps us find the number of different arrangements. Order matters, but once we use an element, it cannot be reused. The factorial symbol, the exclamation point, denotes the product of decreasing positive whole numbers. For example, 5 factorial would be 5 times 4 times 3 times 2 times 1, or 120. Permutations occur when order matters, but there is no replacement. It is similar to the factorial rule, but we are not arranging all the elements, but just a subset of the elements. Combinations occur when there is no order and no replacement. You will note that this rule looks much like the permutation rule, but we must divide by r factorial. This removes the number of ordered arrangements. In other words, all arrangements of the same elements are counted as one element in combinations. This means that the number of combinations will be substantially less than the corresponding number of permutations.